I'm Tao Wang, and we're happy to be back in Santa Cruz. And many thanks for the organizer to give me this opportunity to present our ongoing work on how ALMA unveils the early star-forming progenitors of the red nuggets. This is my main collaborators. Many of them are from UC-HiPACC. So what are the red nuggets? And they are primarily massive and compact quiescent galaxies at ratio 2. But except that they have thanks. Is it okay? Hello? Very high agent fraction. And yeah, they have a very high agent fraction. So despite that, most of them, they don't have much star formation and gas. But really, the agent is still very active in these galaxies. So during the first few years after the discovery of these galaxies, most of the efforts are focused on how they evolve into today's galaxies. For example, in 2013, what they found is that if you do a very nice job on decomposition of the light of today's massive galaxy, actually can reveal there's a very compact core in the center, which is very similar to the profiles of ratio 2 red nuggets. Also, there are a few work also found very similar galaxies in the local universe in terms of the mass size relation. And for example, in this work, they found a very complex galaxy with standard mass roughly 10 to the 11 and the size of 1 kpc. But if you look carefully, there's a prominent disk structure in this kind of galaxies. So we don't have many progresses on the progenitors of red nuggets until the Candle survey, for example, in 2013, and also in the series work of Sandy and Guillermo's work. And we found actually there's a significant population of blue nuggets, which means that they have similar structures compared to red nuggets, but they are still star forming. Actually, if you look at the specific star forming rates of these blue nuggets, most of them they are still on the main sequence. So this is in the field, actually in clusters at this redshift. So this is our recent work in the ratio 2.5 cluster. We found that for the massive cluster star-forming galaxies, there are also, many of them they show very compact structure, which is similar to those red nuggets already. So on the formation mechanisms of these red or blue nuggets, there are a few scenarios. For example, many people are concerned about the progenitor bias because we know that these red nuggets are quenched earlier than the star-forming galaxies at the same redshifts. And so we know that in the earlier time, the universe was denser, so galaxies have more compact structures. There are also a few other scenarios which, for example, the gas-rich major mergers which will cause a central starburst and will form red nuggets. Also, as we heard many talks about the compaction from Avishai and his group. Basically, what is compaction? And here's a direct quote from Zolotov's work, which basically means these early stream-fed, highly perturbed gas-rich disks, they can undergo phases of dissipative contraction into compact star-forming galaxies, either due to major or minor mergers or due to, for example, the counter-rotating gas accretion. So the first question I want to ask is progenitor bias the whole story? Because whether you believe or not, the progenitor bias is always there. So in 2016, Simon Lilly has done very nice work. Basically, they use a very simple model. So if you simulate galaxies, star-forming galaxies, follow the mass-size relation which we actually observed, and then you use a very simple model to incorporate this progenitor bias to see whether they can naturally form a red sequence with these compact sizes. So basically what they found is indeed, if you only consider this progenitor bias and also the differential feeding of the galaxies when they are quenched, so you indeed will form a sequence of more compact quiescent galaxies. But the question is, can this explain all the differences between the blue and the red galaxies? The answer is probably no. For example, here you can see the contrast between the blue star-forming galaxy and the red galaxy. Here's a factor 2 difference. But what we actually observed is like a factor 4 difference. So apparently the progenitor bias has played a role here, but most likely it's not the whole story. So we need some other mechanisms to explain this size evolution or the formation of this compact galaxies. So in simulations, they found similar things. For example, in the illustrated simulation, they first identified some of these compact galaxies, and then they traced back their formation history. What they found is that roughly half of these galaxies, they went through some sort of compaction during their formation. The left two panels, but also some of them, roughly half of the population, it seems they are formed follow this progenitor bias. They are essentially small across all the cosmos time. They're always among the smallest galaxy at any epoch. So this is this can be corresponding to this progenitor bias. So the question is then how do you identify these progenitors in real observations? And so there are a few works that try to search for these star-forming progenitors of red nuggets at a ratio larger than 3, because it's natural. If you want to form a red nuggets at a ratio 2, then you must the star-forming progenitors must be at a much higher ratio, because if, the age of today's ratio 2 red nuggets is around 1 gigayear or so. So that means most stars will be formed at a much higher ratio. So first, they try to see whether those Lama-Bragg galaxies can make these red nuggets at ratio 2. So here is the mass-size relation of the Lama-Bragg galaxies, and then you assume they will continue to form stars at their current star formation rate. Then what will they, where will they be at this plot at the lower redshift? So the conclusion is that it can explain some relatively low mass red nuggets at the ratio 2, but cannot explain those most massive red nuggets, which is quite natural because the LBGs, they are not massive galaxies. The star formation rate is also low. So then where to find these star forming progenitors of the most massive red nuggets? So here, the picture is when I search for blue nuggets, this is the first picture come out from Google, and I think it's useful. So back to 2016, we have performed a search of high redshift UV faint galaxies at the redshift 304, which means basically they cannot be picked up by lemma break selection. So we call them H and ARAC selected extremely red objects. Basically, if you plot the color track of different types of SEDs in this color current diagram, those lemma break galaxies, they will fall in this region. Most of them they will be not showing these red colors, because then you will not pick up with the UV selection. So then, but you do have these red galaxies, and which seems consistent with the color track at the higher redshift. I mean, about redshift 3 or 4. There are some low redshift contaminations. Basically, you can use another. You need to apply another color set to reject those low redshift. For example, redshift 2 to 3 dusty galaxies, and then you will only have these high redshift massive galaxies. So what is interesting is that roughly 20% of these galaxies are completely undetected in the HST imaging. So we can call them H dropouts, which means, but they are, so despite that, they are very bright in the ARAC bands. So basically, you see nothing in the HST imaging, despite that they are in the candles field, which means that they have the deepest HST imaging. So what are the nature of these galaxies? So because you cannot do much for individual galaxies because they are extremely faint, what we do is we did a stacked fine-infrared SED, try to have some sense on their redshift distribution. So if you stack the fine-infrared SED and then you found that the peak is actually around 500 micron. That means most of the galaxies, they are likely at the redshift 4 also. But this is only from stacking. So we want to confirm whether this is true for individual galaxies. So then we propose an ALMA proposal to detect the 870 micron emission these galaxies. So this is the HST imaging of this subsample. Basically, there are nothing in the ARAC in the position of the ARAC emission with the 2 hours integration, basically. But with ALMA and with only 2 minutes, basically we detect all of them. And the median flux is around 1.6 millionsky. So they're relatively bright, but not as bright as the conventional SMG population. It's usually 3 to 5 millionsky or even brighter. So then the answer is yes, we do miss some of the most massive galaxies at this redshift from HST. And we can only reveal them with ALMA and of course with the JWST in the future. So with this observation, what we can do is also another thing that we can do is to measure the size of the ALMA emission. So although we propose for 1 arcsecond resolution observation, that in the end they observe 2/3 of the sample with the 0.2 resolution. That means we can measure the size accurately for this subsample. We do this fit in the UV plane, and here you can see the one example of this profile fitting. If it is an unresolved source, then it will appear as a flat curve in this plot. So then you have the size measurements for 2/3 of the sample is around 40 galaxies. And you can plot them in the mass size relation and compare it to those, for example, the redshift 3 mass size relation in the optical, restream optical wavelength. Here is the mass size relation for the star-forming galaxy at redshift 3, and here's the quiescent galaxy. You can see the size of these galaxies, the H robots actually is already consistent with the red nuggets, even at this higher redshift. So if you evolve these galaxies into lower redshift, assume the track in this diagram is like this, which is proposed by Van Dock in 2015. Then basically they will move here with stellar mass roughly 2 times 10 to the 11, and with the size around 1 kpc. So that's consistent with the mass-size relation of this with the ratio 2 red nuggets. Also, the number density is also consistent. So if you see the stellar size or the size in the rest of optical may be larger than the star forming region, and then we try to, for example, from Barrow et al., they found that actually the ALMA sizes is 1.9 times larger than the optical sizes. It's smaller than the optical sizes. So if we multiply by this factor, we can still get that this galaxies are still consistent with the progenitors of the red nuggets. So the next step is to do spectroscopic information for this galaxy. It's really challenging. And for the first step, if we first identify some most promising high redshift candidates with extremely red sub-millimeter color to propose for ALMA line scan in this cycle. Hopefully we will detect some lines. So of course, the GWST will be more efficient, and we really hope we can get more information in the near future. Okay, so here's the summary. So basically, with ALMA, we found that there's a significant population of massive UV-faint galaxies with surprisingly smaller sizes, and are likely the star-forming progenitors of the red nuggets at retro 2. Thanks. So I think in terms of that, it's not that different. Like how you explain the retro 2 blue nuggets, how do they form the red nuggets? And the same is the same scenario. And right now it's really not that clear. For example, from the MOSFER spectroscopy, we know that it seems the gas content shouldn't be that high for these galaxies. But then with some ALMA observations, we do find a lot of gas reservoir. So really now the situation is not clear how will they evolve in the near future.
Try to estimate their contribution to the conference
Yes. Roughly 15% at ratio 4. 15% of the current estimate.
I must say that it was not done convincingly so far, but my first estimates are that they are. So they're pretty much consistent. This is 2, 3, given the period, the lifetime of blue nugget that we reduced to observation. Pretty consistent with everything that integrated later in terms of red nuggets. But it's an open question. I think that